Another tough circular maximizing question. So let's have a look at this one. ABCD is a trapezium with AB is CD. So that means that that is the same as that, which I think is called an isosceles trapezium. The vertices are on a circle with center O, radius 4 units. So line segment AD is the diameter, which we'll note down is 8. Find BC in terms of theta. So we need to find BC, this distance here, in terms of theta. So the strategy for this one is going to involve us trying to work out one of these lengths. And what we're going to do is use some circular or some trigonometry to get that. Now to do it, what I need is an angle in here to work out the length of this here. And unfortunately, I don't have an angle in here. And they want it in terms of theta, so I need theta in here. So the rule we're going to use is this one that you would have learnt back in year 8, and that is that if we've got a parallel line, so these lines here are parallel, if you've got a line intersecting through the parallel lines, this angle here, theta, will be exactly the same as this angle here, theta as well. Okay, I think often called the Z rule. I've heard it called that before as well, but anyway, so that basically means that these two angles will be exactly the same as each other. Right, so from there, what we can actually do is get BC, because what I'm going to note is that BC on 2, okay, this length here is going to be BC on 2, or half of BC, is going to be the, what do we got, adjacent over the hypotenuse. Okay, so I've got cosine theta equals the adjacent, which is BC on 2, over the hypotenuse, which is over 4. Which actually is going to be the same as BC over 8, okay, is cosine theta, and that means BC is going to be 8 cosine theta. All right, so find BC in terms of theta, done. So part B, so that's A. Part B is going to say, or going to involve us finding the area of a trapezium in terms of theta. And what I'm looking at here on my desk is the area of a trapezium formula. So let's just call it A of theta equals half A plus B H, where one of these length is A, one of these parallel lines is A, one of them is B. It doesn't really matter because they're being added, and we've got a height here. So we can already start to fill in a few things here, which is half. I know this length here is going to be 8 plus this length here I know is BC is 8 cos theta multiplied by the height. Now that's what I've got here, or what I need. Okay, and we're going to use the same thing to get height. So this is the height here, which is the opposite over the hypotenuse. So that's the sine. So that would be sine theta equals the opposite, which is h, over the hypotenuse, which is 4. That means the height of this trapezium is going to be 4 sine theta. So times 4 sine theta. Okay. All right, so let's see if we can tidy this up a little bit. And what I'm going to do is A of theta equals, so I might just throw the half in there, and that's going to be, so I'm going to put 4 sine theta out the front, and I'm going to halve these, which is going to be 4 plus 4 cosine theta. All right, now what I'm going to do is, well, I've got a couple of options here. Should I take the 4 out as a common factor? Not sure, let me think. Okay, what I think I might do is just yank 4 out of that, and so that's going to be 4 multiplied by 4, which is 16 sine theta, multiplied by 1 plus cosine theta. Okay, let's start to get its derivative. So this is going to be the product rule here, where u is equal to 16 sine theta and v is equal to 1 plus cosine theta. Okay, du d theta is equal to 16 cosine theta, and dv d theta is equal to 1 chops out, negative sine theta. Okay, let's get its derivative. So a dash theta is equal to u dv dx, which is negative 16 sine squared theta. So that's u dv dx plus v du dx, which is going to be 16 cosine theta multiplied by 1 plus cosine theta. Okay, let's clean it up. So I'm just going to distribute that, plus 16 cosine squared theta. All right, where to from here? Okay, so what we'll do is we'll further factorize this derivative function. So let's grab 16 out. And what I'm going to do is write cosine squared theta, take away sine of theta all squared, and I'm going to add plus cosine theta onto the end of that. Now what I'm going to do is use a particular identity on this that's in your notes. Okay, so have a look at your notes under the Pythagorean identity, and you'll note that there's something that we can do with cosine squared theta, take away sine squared theta. And what we can do with it is actually replace it with something else. I'm going to pause the video and pull up the section of the notes actually. Okay, so here it is. I'll just swing it in now. So I've just got written down there. That's not a good sign. We've got two identities or two versions of the same identity here. So if I've got cos squared or cosine theta all squared take sine theta all squared, I can replace it with this thing here. And we go on, or I've done that bit prior to this and it's shown you why or how. So let's do that. We're going to replace it with that particular expression because they're the same. So it means the exact same thing. Okay, so I'm going to go and do 16, and I'm going to write, instead of that, 2 cosine theta squared, take away 1 plus cosine theta. And what we're going to do at the same time now is let it equal 0 because I'm trying to maximize. I'm going to dump the 16. So that's going to be 2 cosine of theta all squared plus cosine theta take 1. Now, what can we do here? Well, actually, we can treat this as a hidden quadratic. Okay, so I'm going to say let a equal the cosine of theta, and I'm going to note that this is then 0 equals 2a squared plus a take 1. Okay, so now what I can attempt to do is factorize this quadratic here. So I've got 2a and a, and I have got, I need to make that, so that's going to be 1 and 1, and which one's going to be negative? We need this one to be negative. So I've got 0 equals 2a take 1, a plus 1. All right, now let's go ahead and solve. So what I'm going to do is sub the, or let's just solve for a. So a equals a half and a equals -1. So I'm going to resub a back in. So cosine theta equals a half, cosine theta equals -1. Now what we're going to do is solve these. Okay, so what are my solutions over here? So cosine, when is cosine -1? It's over here. So theta equals, what's that? That is pi. When is cosine 1/2? Well, we're going to start here, and cosine is going to be there at pi on 3. That's when cosine is going to be 1/2. So theta equals pi on 3. Now, it's also 1/2 there at what's that, 5 pi on 3. But if you consider what we're actually looking at here, this theta value here is got to be between 0 and pi on 2, or 0 and 90 degrees, for it to be an appropriate one. So actually we're going to say here, but theta is an element from 0 to pi on 2, therefore theta equals pi on 3. And I'm guessing we have to find the area. So find the area of the trapezium in terms of theta, and hence find its maximum area. So all we would do at this point is, and I'm running out of room fast here, but I'm just going to do it over here. I would do A of pi on 3. So slam pi on 3 into your area function, which is this thing here, and see what you get. So let's work it out. I've got 16 times the sine of pi on 3, which is √3 on 2. And that's going to be all multiplied by this one here, which is 1 plus the cosine of pi on 3 is 1/2. All right, so what I'm basically going to get is 16 √3 on 2 times 1 plus 1/2, which is 3 on 2, which is then going to be 8, 4, 1. What do we got? 12 √3. Okay, that's going to be our area, and it's going to be units squared. All right.